Hi guys, we're here to talk a little bit more about absolute dating. So, how we can date geologic information very precisely rather than just saying, oh, this is older than something nearby or younger than something nearby. So, we already talked about general radiometric dating using radioactive decay and half lives, but we're going to talk about a couple other techniques that can help us try to do this same process. So, let's open up the screen here. Okay, so the first technique that I want to talk about is within the field of kind of paleomagnetism. So we already talked about in the context of plate tectonics, the fact that the Earth itself forms a giant magnet. So the outer core of the Earth has this fluid iron layer that creates an electrical conductor. So it's this giant magnet. And we also mentioned that when a fluid version of a rock, so like a magma or lava, cools down, as it drops below the temperature of 500 degrees Celsius, it will start to line up with the Earth's magnetic field. And so this is why different rocks have magnetic powers. That's what magnets are, these magnetized metal pieces or kind of geologic pieces. And so the alignment of the different kind of metals like iron within the rocks shows us the direction of the Earth's magnetic field. We also learned that the position of the Earth's magnetic field, or the direction that the magnet is oriented today, is actually not the same way that the Earth's magnetic field has always been oriented. And we know that, in fact, the Earth's magnetic field has flip-flopped over time or experienced these reversals in polarity, where what we think of as the North Pole today has been flipped. And so I actually am not quite sure about this off the top of my head, but I'm pretty sure that today the South Pole is actually sort of like the positive side and the North Pole is more like the negative side of a magnet. But the point is that it has not always been consistent. It's flip-flopped and not on a particularly well understood pattern. And so we've had these different periods of what we call normal polarity, where rocks that form are in alignment with kind of the current polarity of the planet. And then we also have rocks that have formed during periods of reverse polarity, where the magnetic orientation within these rocks is opposite of what we see today. And so we saw this pattern in the oceans. We started to make maps of the magnetic strength of the ocean floor. And that's one of the things that helped geologists understand that new ocean floor was emerging from these mid-ocean ridges because of these magnetic patterns that were symmetrical around these volcanic ridges within oceans. But this is also something that can help us kind of figure out when different rocks were formed based on the polarity that is contained within these rocks. So this is just kind of a pattern showing how they figured this out by looking at the ocean floor. They would look at the strength of the magnetic field, and when we were on top of rock that was formed during time periods that align with the current polarity of the Earth, the magnetic field was stronger because the magnetic field of the rocks and the magnetic field of the current Earth align, and they kind of add together to create a greater magnetic field. And then on the other hand, if you're sitting over a rock that was formed during a period of reverse polarity, then the magnetic field is weaker because that magnetic field of the rock is kind of counteracting the current polarity of the planet. So anyway, this is the pattern that exists within the oceans as the rocks that form are pulling away. And so they're kind of spread out horizontally along the ocean floor. But in many cases on the Earth's surface, what we have is many rocks that are vertically stacked on top of each other that have these different patterns of polarity. And so we can think about which direction the polarity within the rocks is oriented. It can help us understand the time period, or at least kind of capture within what time period would have been possible that this particular rock formation could have been forming in. So for example, here is a cliff that contains different rock strata, right? These different distinct layers. And then we can look within the rocks and see If the rocks contain reverse polarity or normal polarity, we can see how they line up relative to other rocks around them. And then that can help us kind of nest when those particular strata formed within the pattern that we understand of normal and polarity reversals that have existed on the Earth's surface. So it can kind of help us, as long as we can kind of ground truth these patterns with radiometric dating, then we can help us understand the magnetostratigraphic age of these different layers. And then I actually don't have a picture of this, and we'll talk about this more later on, but interestingly, as the continents have actually moved around, moved their position, of course, the orientation of a continent relative to the North Pole has also been changing. So maybe if we have, the North Pole up here and a continent here, and then currently any lava that flows out would line up pointing towards the North Pole. If the continent previously was positioned like this, we might find that the polarity of rocks is pointing in a direction that doesn't really point either towards the North Pole or the South Pole. And so when this was originally discovered, there was a lot of questioning about like, oh, why are the poles wandering around? And what we've kind of discovered is that these different directions that polarity of rocks contain within, or this orientation of polarity does not actually represent a fact that the North Pole has been moving around, but it represents the fact that the continents have been moving around, which is kind of a further evidence to support this concept of plate tectonic movement. So anyway, we'll talk more about that later, but all this is to say we can look at these different patterns of magnetic polarity within rocks to help us understand the time and what was going on during the time when they formed. So that's an additional technique that's used by geologists. And then the final thing I want to mention is fission tracks. So fission tracks are basically these kind of scars that occur within the crystal structure of minerals. And the idea is that in certain minerals, when this radioactive decay process occurs, which we talked more about before, as the atomic particles are being ejected from the atom itself or from the nucleus, they actually can create a fission track or like a scar in a nearby crystal. And the more time that has passed, the more of these little scars or fission tracks are created. So an additional way that we can date these materials is we can look at the accumulation of fission tracks, and we can look at this process in laboratory environments to understand the rate at which fission tracks are created. And then we can kind of expand that out to imagine, okay, well, what if we had a lot more time? How many fission tracks would be created? And we can use that as an indirect way to help us estimate the age of these different materials. So that is an additional way that you can go about doing this. And then finally, I just want to give a shout out to Scott Marshall, who is a professor, geology professor, and he has some really cool resources on his page, and I actually stole one of the slides from him. So in the effort to be plagiarism free, I want to give him credit and recommend, if you guys want to learn more, you can check out some of his resources. So, all right, that's what you need to know.